So from our most recent definition, so I gave out the definition earlier, and then we took a pause on that for a little while, right? We took a break on that for a little while. So I'm just going to remind that definition. Say that x, right? The continuous function. That was the definition we were talking about. So I also gave some graphical illustrations about its accumulation. So in my illustration that we had last time, I talked about, so we were trying to approximate that area, right? That area under the curve, and that prop specifically was the function f of x equals x squared. And so to get that area, the idea of using integral now is that think about when you're at any one particular x value here, you can draw a stripe. So that stripe itself has a very thin and infinitesimally small change in distance, right? In a very thin thickness again. So just that, right? The thickness is the differential dx, okay? And that's why, and the function height here, right? That height there is the function value at x. So, and that's why height multiplied with thickness, right? We're accumulating. And that symbol is now accumulating all of those stripes areas from A to B to there. We get so for this problem we apply that we get the area. Okay? So that's why one stripe, it got some thickness. The next stripe over it gets thicker and thicker, and so eventually we keep doing that. You see how I keep drawing those stripes, right? And the height of the stripe, the height of my stripes keep getting changing depending on where my x value is, because at different x value I have a different height of the stripe. You see what I'm saying, And so the integral is accumulation. But now, before we go on really far, I gotta mention it. So it's natural like that. Anytime to get started into integral and have a solid understanding, any instructor, including me, use the example of area. Okay? And then for this particular problem, yes, doing the integral. So for our particular case here, the function is f of x, right? And so for that area here specifically in this problem, the integral is accumulation from 0 to 1. It's the interval. And your function now is just simply x squared dx. See what I'm saying now? Okay? But now I have to emphasize one thing that, so area is a good place to bring in to illustrate the idea. But now we have to take one particular remark here, a very important remark. And I also mentioned that earlier. An integral, right? An integral like this does not always mean, so this symbol of mine here does not always mean an area. So, because usually when we use this example right here, people would tend to think that anytime you come up with an answer for an integral, it's going to have to be an area, but nope, it's not. An integral itself right here, as a matter of fact, just like what I wrote down on the board, the integral itself can simply just be a Riemann sum where we're taking the number of sub-intervals go to infinity. Okay? Because now just think about the height here strictly as an area. If you are talking about an area, then that, or in a better way of saying it, if we tie ourselves down to an integral has to be an area, then that means those stripes, these things are here. Those stripes from your curve has to always be vertical and positive height. See what I'm saying now? But that's not the requirement of this Riemann sum here. Nobody said that the Riemann sum, the height f of x star has to be positive. Okay? As a matter of fact, who knows? In some days you're doing some kind of function where some part of the graph stays above the x-axis, some other part of the graph stays below the x-axis. And so, according to the Riemann sum, all we need is just the height, right, of the stripes multiplied with thickness. Height of the stripes. In some area we got positive heights, right? But then some other area we got, some other zones of the function we got negative heights. Those f of x star outputs here, right, being negative. Okay, so in the end, truly, an interval is simply just a Riemann sum where we technically the number of subintervals goes infinitely large. Okay, and that's the idea of an interval. That's why it's strictly just accumulation. It's accumulating the function's value multiplied with thickness. Function value multiplied with thickness. Area is only one application, one among infinitely many applications that we're using interval for. Okay, and that's the idea right there. And so now, after taking some explanations of mine right there, let's look at a couple. And I didn't really show any method for how we calculate the interval yet. And pretty much for now, think about it. This is the only way. Because we've got to set up an interval, and we've got to set up a Riemann sum and take the number of subintervals to infinitely large, right? Let's get to that later. But now, let's look at something like this. In this way right here, let's look at example 1, and that will illustrate some of the idea. We want to evaluate, really get the exact answer, right? Evaluate the interval 0 to 3, the function here is 3x plus 6. Yeah, okay? We want to evaluate that. But then here's the instruction by interpreting this interval. So interpreting it as an area. Okay? See what I'm saying now? Because again, the reason we are doing this, we did not have a formal method of calculating it yet, okay, other than just accumulating the Riemann sum together. And so, now before we get into this example, what does that mean by we want to get the exact answer of this interval by interpreting it as an area? So, here's how we're doing it. At least for the function itself right here. For a function itself right here. For this function itself, the function is being the f of x being 3x plus 6, right? You guys agree with me on that, okay? And so I may be out of scale right here, but 3x plus 6, when you are graphing it, right? And you don't even need the advanced decimals or anything like that, but think about 6 as being here somewhere, right? With that scale, and then being 3x plus 6, so it has to be a positive graph going up. You guys agree? Okay? And like I said, forgive me if I'm out of scale or anything like that, right? But 6 is here, and the slope is, right? Going the 3 up, right? 1 over 3 up. See what I'm saying? No? And so, in this way right here, with my function, then going from 0 to 3. Why is it 0 to 3? Because the interval is doing that. The interval is asking you to do the accumulation. All you need to see here is accumulation of stripe with height being determined by this rule. And the thickness is dx on the x-axis. And then the accumulation happens from 0 to 3. That's what it is. And that's why back in the picture, I am going to show, I'm going to show from 0 to 3, about here, right? 0 to 3. You guys with me on that, okay? So we have, in the end, we have this picture. So the accumulation goes like this. Stripe, accumulate with another stripe, keep accumulating. See what I'm saying now? Okay? That's the idea. So expectedly, whatever after we finish the accumulation, that's our total integral value. Okay? That's our final integral value. But now, so what's up with interpreting it as an area? The idea now is that at least for this function, what you can see is the function here, f of x, stays positive, right? Or at least equal to 0 inside of, for x being inside of this interval from 0 to 3. Do you agree with me on that? Okay? The picture is telling the story, right? And so that's why, if it's positive like that, then yes, this particular picture that I'm attempting to make those stripes accumulation like that, it does represent a real area. See what I'm saying? No? Okay. It's just the reason, right? At first, I mentioned that we don't always think of the interval as an area simply because there will be times your function sinks below the x-axis, like some area here, your function. But in case you're in your interval and it takes the interval over an interval where your function is already positive, right? Then you can think of that final result as an area just fine. See what I'm saying? No? So we can put that as a second remark right here, as a generality right here. So as another remark, that if your function f of x is greater than or equal to 0, right, on the interval, the closed interval from A to B, then the interval from A to B, right, on this function equals the area. So equals the area. When I say the area, I hope you see what I mean. The area underneath the curve, right, under the curve between the curve and the x-axis, and in between the two values. Okay, so yes, the function can go all over, but at least in some interval it stays above the x-axis, right? And that's right, this area right here. Yes, that can be equal to the integral from A to B function. That's why pay attention to that. We can only legally think of that as an area when the function is known, right? When the function is known to be a positive or at least 0 inside of that given interval. Sounds good? Right. So that's generality. So now I'm going to use from this recognized generality. I'm going to use that into working with the problem. So now we can see in this problem right here, the intervals particularly from 0 to 3, right, for the function 3x plus 6 dx, it is going to be the area, right, of the shaded. So now I'm going to go ahead and make some shaded. You guys see what I'm saying now? The area of shaded region, right? That's the plan right there. And that's what it means by, so I'm trying to break it down to explain the wording of the problem, but that's what it means by we're calculating this by interpreting it, right, as an area. Sounds good with that, like that. All right, so now once you've gotten the idea, then at this point we are ready to find the final value of your integral. So if we think of that as an area, then what figure is this? What kind of shape is this? Trapezoid. It's a trapezoid, right? So how do we find the area of a trapezoid? Somebody in this class, which word you might hear before? How do we find area of the trapezoid? Somebody hear it?
Top plus bottom.
Top plus bottom. Now, which one here is top? Which one here is bottom, by the way?
Doesn't matter.
It does matter. What's that? Now, for a trapezoid, in his way of wording it, right? For a trapezoid, top and bottom means those two sides are all parallel. You guys with me right there?
Yeah.
So it does matter. Because for trapezoid, not all sides are parallel, right?
What I meant was that the top could be the bottom, the bottom could be the top.
Right, but so now in here, which one is which side? Which two sides do you call the top and bottom? These two. See what I'm saying? No? Okay. So now yes, you can pick one, right? How big is this height right here? That height is 6. You guys agree? Okay. How big is this height? 15, right? Yes, because it's just, you see, substitute 3 into the function. So it's 15 because it's equal to 3 times 3 plus 6, right? How about let's just make it short, right? The function value of 3. See what I'm saying now? Right? And so you got top plus bottom, just like that, right? Top, and so 6 plus 15. How big is the height? Which one do you see as the height here? Okay. The height is right here. That top side. See what I'm saying now? Okay. So the height here is equals 3. Okay. This trapezoid is standing sideways right here. So we multiply with the height to be 3, and then we divide by 2. Now that's getting us, that's making it ready for the final answer. So you guys can go ahead and do the math. 31.5? Okay. 31.5. Alright, so yes, we have found that actual answer again. Sounds good? So when it comes to this kind of problem, the reason I try to explain so carefully because back to the problem, once again, I want to mention that at this point we did not learn, you guys have to understand, we did not learn any formal method of finding it. So the way we solved this, yes, we got the exact answer, but we were just beating around the bush. See what I'm saying now? Okay? Because the real work is here. You have to set up, you have to break it down into a few intervals, right? And then keep increasing the number of intervals so eventually you get that total accumulation. That's why it's so deadly. Right? And you guys didn't even get into that real kind of problem yet. And that's why we want to solve this problem we want to find the exact answer to this integral by interpreting it as an area. But now see, doing this, taking this route right here, finding an integral final value by interpreting it as an area, you got a couple of requirements to check. Okay? Those requirements I mentioned earlier. Now I'm going to summarize it. The first requirement is you got to ensure that the function, right, stays above the x-axis, being positive at least in that interval, okay? In that integration interval. See what I mean? Right? Because without indicating that, right, without being sure about that, right, then you're not even allowed it. It's not even legal to proceed with that method. Okay? See what I'm saying? No? Okay. But then really, I'm making it like a big deal about you got to prove it. But as far as all you need is basically having a graph, right? And the graph can tell the story. You see what I'm saying? No, you don't have to formally sit down and prove that hey, the function is above the x-axis, being positive in that interval. Just simply like throw in the graph or something like that, right? And that will whoever read your paper will understand. You got the idea? Okay. So now once I pointed out those highlights again, right? Then we can pretty much repeat the example. Or in a different problem, then you guys can get into a better handle of that. So we can call that example 2 right here. 9 minus x squared. Yes, okay. Pretty much the exact problem, but we're looking at a different function to integrate. So in this integral, what we recognize is that the function is square root, right, of 9 minus x squared. And so I raised that question earlier when I was erasing the board, but what do you recall about the graph of this function?
It's like this.
Okay.
I don't know. I can't picture.
What's the worded description of that? You got that right. The description right there. It's a semicircle. Right? The equation for that. I mean, the equation for any circle is, and by the way, it's a semicircle center at 0 to be precise. Okay, center at 0. And then with the radius here being 3. You what I'm saying, no? Because for a circle, for a complete circle, center at 0 with radius 3, then we're looking at x squared plus y squared equals 9. See what I'm saying, no? Okay, so that's why, see this thing here expressed that as a function of x, right? That means that right from here, you guys can subtract x squared from both sides and give me xy squared equals 9 minus x squared. We're getting closer to it, aren't we? Okay, and then take square root both sides. And technically, it gives you 2 square roots, right? Plus and minus square root of the 9 minus x squared. But since the function here only takes a positive one, right? That means, see, it's the upper dome of your semicircle, of your circle. Okay. Or in other words, we call it it's a positive semicircle. Sounds good? Okay. And so, now what's my point of bringing up the graph right here again? That's your function, right, over the integration interval right there, minus 3 to 3, and see, so now with the graph being drawn, right, does it match this requirement right here? Does it satisfy this requirement that the function stays above the x-axis, being positive, right? At least inside of the integration interval. See what I'm saying now? Because our integration interval is from minus 3 to 3, right? That's what's being indicated on the problem. So back to that beginning problem right here. You see the low number and the high number that we attach to the symbol right there, right? We call it as the integration interval. Okay? Right? The interval that we're taking the accumulation over. Sounds good? All right, and so now that's why, back to the picture right here, yes, clearly it's positive, right? The function is positive inside of that integration interval. That's why making the accumulation will definitely produce the area, right? So what kind of area is this? It's the area of a half circle. You guys following? Okay. And so now all you see here is this circle here. Now all we need to do is just to identify the characteristic of the circle, right? It's got radius 3. You guys agree? Okay, and that's all it needs. Okay. So now we have found an answer. The integral from minus 3 to 3, right? The definite integral from minus 3 to 3 on this function, square root of 9 minus x squared. Right? Taking that accumulation right there will produce the area, right? And I don't think I need to beat around the bush anymore. But that area here is simply going to be what? Now, what's the formula for area of a circle?
R squared.
Pi r squared, okay. Pi r squared, so in our case, here, r is being 3, right? So that means times 3 squared. But is this the right answer? I mean, the correct final answer? What's missing?
Multiply by 1/2.
Yes, because we only go half circle. You get that? Okay, you guys done. So it turns out exactly 9 pi, right, over 2. Right, that's how we find it. So we only took account of our understanding about the integral as simply as infinite accumulation, right? We keep accumulating it. And then for our problems here currently, we take advantage of the fact that the function stays above the x-axis, being positive. That's why we can interpret that as an area and calculate and come up with a final exact answer. That's what I'm explaining with that. But in the end, this is not the official. It's not the universal method to find any integral. Because what about there's some integral where some part of the function is sitting below the x-axis and say above the x-axis? We didn't find that yet. Well, so okay. So 2 examples along this line should be good enough. Let me swing over to the other board, okay? And then I'm going to bring up the third integral. This time the real work begins. And I have left this here long enough. Can I erase that then? Because I need, at this point for this problem I'm about to bring up, I need as much space as I can. Okay. So let's now call that example 3, right? But really, we're going to really evaluate the integral 0 to 1, right? Of the x squared function. Okay. So, first of all, quickly as a development of the problem here, see your function is x squared, right? And your integration of interval is here, from 0 to 1. So really it's just this interval again, right? And making that accumulation, you're going to get this area. Well, the function is still above the x-axis anyway in that interval. You guys follow? So, calculating that infinite accumulation, right? Formally, it's the integral. Calculating that exact integral, we're going to get the area of this curve, underneath the curve between the x-axis. But see, I only told you guys before this point, I only told you guys that this area equals 1/3, but we haven't found out why. See what I'm saying? Now, I only told you guys. Now this is where we're finding out why. Okay. See what I'm saying? Now, I'm talking about the exact answer being a 1/3, right? But so far I've been only telling you guys. And that's why for this problem here, and so what does it mean by using the limit definition? You see, because an integral is a Riemann sum, right? Where we, as a definition, a definite integral is a Riemann sum where we take the limits, right, of the number of subintervals increasing to infinity. That's the idea of that. So we really have to do the real accumulation work. Okay. So now let me take away the picture. So I brought this up. I mentioned this briefly here because I want you to understand. We already have a known final destination for that problem, right? Being a 1/3, that's our final answer right here. So that's a way to check our work. But as far as the real work here, you see the integral from 0 to 1, right? For this function x squared, by default, we're setting up a Riemann sum. See what I'm saying? Your function is the squaring function, right? That means we're going to take a whole bunch of, and then here's the thing, a whole bunch of sample points, right? A whole bunch of subintervals, and we take a sample point in each of the intervals, and then we square the sample point, because that's now the function evaluated at the sample point. You guys see what I'm saying now? And we multiply with a delta x. Agree? Right? And then we're summing up all of these from 1 to whatever the finite number of subintervals, right? And then after that, as order operation, after that, we take the limit operation, allowing n to infinity. That's the starting point. You want to see, say that. Okay? That's the starting point. And so, but now, with a starting point like this, then good luck with that. We got nowhere to move on here. So we gotta go further into the details. We're gonna start breaking it down into detail. We call it about delta x here. Okay. What's known about delta x? Delta x is always the final point of your iteration interval minus the initial point, so 1 minus 0 over n. You guys agree on that, okay? Okay? So delta x is always 1 over n for this problem, because the interval, the iteration interval is from 0 to 1. So that's a rule like that, right? You guys already knew it. Okay? That's 1 over n, so we got some known facts. But I'm still putting the pieces together, I'm still diving into the pieces. But see, the x star I right here is just the general sample point. When you're breaking your interval into so many sub-intervals, right? And like the idea that you have already seen, the sample point can be really anywhere. And there's no necessarily a hard rule about where to find those sample points in each of the interval. And so that's why there was a left Riemann sum and the right Riemann sum, so that we can purposely set our sum into a rule, right? So that keep things easily organized. Am I making sense? Okay. And so at this point right here, using a left endpoint rule or the right endpoint rule or the midpoint rule that I showed you guys, okay, it's just only an option. So it's just me, I work more naturally with the left endpoint rule for some reason, right? But I highly recommend that on your own time at home, you guys repeat the exact same example using the right endpoint. So how about right now I'm using LN, okay? And then like that's what I said right there. On your own time at home, repeat the examples, but at this starting at that step, use RN, right? And also it's even better that you use MN, okay? Do both. You know what I'm saying? Huh? So if we're using the left end point, okay, then this is how the formula, this is how the Riemann sum becomes. So the interval from 0 to 1, right, on your function x squared dx is the Riemann sums where, so each of the x star I, right, now has a clear indication. We're talking about xli. Remember the xl, the left end point on each I interval, right? And the function says we square each value. That's why it's xl squared, xli squared, right? Now the delta x here, I have my legal right to put that as a 1 over n. You guys following? Okay? And then I is running from 1 to n, and we're taking the limits. It's n, infinity. Any questions? Okay, so in that way, now, do you recall that that generality about xli with you? Xli is always what? X of 0, right? Plus I minus 1 times of the delta x. Remember that general regulation right there? Okay? Putting the pieces together. And so that means we even have to tear this down even into like further detailing, deeper detailing here. For our particular problem, the overall interval is from 0 to 1, right? The iteration interval from 0 to 1 right there. So x of 0 is this value. You guys agree? Okay. So that means it becomes 0 plus I minus 1 times the delta x. What did I say about the delta x? 1 over n, right? So 1 over n. That's how it would. Or in other words, I can just rewrite all of this here as an I minus 1 over n. Are we good with that then? Okay, so I'm going to bring this. So this is a general representation of each of our xl I. Right? The left hand point at any I is the interval. So now I'm going to bring that and substitute that in here. So the Riemann sum now becomes, we got the sum here, I running from 1 to n, right? So now I'm talking about I minus 1, right, over n, all squared times 1 over n. Okay? And then we want to take the limits as n to infinity. Sound good with me on that, right there? Okay. Go ahead, take some time to get yourself caught up with the work I'm doing up here. All right, ladies and gentlemen, ready to continue? So I'm going to adroitly rearrange the terms inside my sum a little bit, just for some good purpose. So the Riemann sum here becomes I minus 1 all squared, but all over. Now see, the square here gets distributed with that n, giving it an n squared in the denominator, right? But with another n squared right here. See what I'm saying? Huh? So I have, with another n right here, so we got n cubed, right? And then this is I minus equals 1 to n, taking the limits from n to infinity. Okay? So You guys recall in the earlier lecture, as a matter of fact, just yesterday I was training you guys in that skill. This is a sum right here, right? And we try to come up with a general expression of that final sum right there. Because in a sum like this, the I is the changing component that depends on your I index, right? But the and really is independent. Yes, the and the and here matches up exactly with that and, but in the end, relative to the sum, the and cubed right here is independent. See what I'm saying? No? So this is what I can do. So from that and right here, right? So my plan is to come up with a general expression for this sum before the limits, before taking the limits. That's the plan. Okay. That's why I'm still hanging the limits here, okay, for n to infinity. But I'm going to factor out a 1 over n cubed, right? And my sum is left behind with this, I minus 1 all squared. So you guys following? Okay? And we keep making it simpler and simpler, didn't we? Okay? Alright, and so now, further. Remember that the I minus 1 all squared can be FOILed out. Okay? And at this point, the I minus 1 all squared is completely free from the ants, right? So it's containing only the changing components in there. So now, in my next step, I'm going to FOIL it out. So I minus 1 all squared is going to become I squared minus 2I plus 1. That's the term, right? That's each of the term of your sum right there. I will run from 1 to n, and then here we multiply with 1 over n cubed, and then we take the limits. Limits will always be the last step in our process. Okay? Are you guys with me on that? Okay? Very important work. And so now I'm going to swing over to this board because we didn't have enough space there. And so now that's pretty much good for us. That will become, so we have a 1 over. One more time, I'm going to write it. I'm going to break down the sum here. We can think of that as one summation on the I squared term. You guys agree with me on that? Minus one summation on the 2I term. Okay? And plus one summation for the constant term 1. Yeah. And these are all I running from 1 to n, I running from 1 to n, and I running from 1 to n. Okay? And then yes, at the end, we're going to ultimately take the limits to infinity. That's how we keep doing the work algebraically. And then that's the reason why I had to spend a day or so, like one complete lecture, is having you guys get comfortable with manipulating around with summations. Okay. So in the next step right here, in our work that we have already learned, yes, limits is here, of course, hanging around. And the 1 over n cubed is a common factor. Now, what did we learn about? What did we learn about a special formula? The general representation for I squared over here. Isn't that? It's the n times the n plus 1 times the 2n plus 1 over 6. We've learned this from earlier learning, right? And now that's how we make use of that. And then this thing right here, it's 2i, the 2 here is it's another independent component. It's the coefficient of your term, right? It's a constant coefficient. We can pull it out front. So now, so bringing that 2 out front, and you just simply looking at the summation of I, right? So summation of I here from 1 to n here, it gives you n times n plus 1 over 2. Remember this? Okay. So from that result, I'm going to bring it in here. So making it n times n plus 1 okay, over 2, but multiply with that extra 2 that we treated as a coefficient in front. See what I'm saying then? Okay. And then there's one more step. What about that last summation? It was a summation of the constant term 1, 1, 1, and 1, right? We're adding up 1 n times. Okay? So that means the last term here produces for me 1 times n, which is just simply n. You guys agree there? Okay? And so now, what's the good thing about the summation? Let me erase the limits here, because I wrote the limit symbol too soon. The idea is, even before taking the limits, right, your summation turns into a general expression in terms of n. That's dependent on the, and remember, n is the number of sub-intervals that you guys are breaking down in your intervals. See what I'm saying? Huh? Okay. So we have successfully expressed our Riemann sum, right, as a general expression in terms of n, in terms of the number of the sub-intervals. And that's why now on top of that, after having all of that done, on top of that, we're going to take the limits allowing n to infinity, meaning we're going to start increasing the number of subintervals, okay, to infinity. So all of a sudden we realize it's becoming just a simple calculus 1 problem right here. You find the limits, infinite limits, right? The limits at infinity for some kind of function in terms of n, okay? And so let's distribute this 1 over n cubed for each term right here. Distributing this into the first term, the n cubed cancel with the n. You guys follow it? Okay, that gives me an n plus 1 over 2n plus 1 divided by 6n squared. That's the first term after multiplying with 1 over n cubed. Do you agree? Okay. The second term here becomes the n 1 over n cubed multiplied again. And by the way, we cancel out that 2, right? And so it's going to become something like this: n plus 1 over n squared. Do you follow? Okay. That's the second term in terms of n. Right? And then the third term is really just, see, 1 over n cubed times n, right? That gives me just a 1 over n squared. And now with something like this, we're going to go ahead and take the limits as n go to infinity. So I'll do again that again. Right? And we got 3 terms, right? Yes, they may look big, but it's okay. It's not so bad. 3 terms. 1 term, 2 terms, 3 terms. Agree? Okay? So that means we can, according to the limit laws we learned back in Calc 1, and you guys freshly came out with me from Calc 1 with that, right? Limit laws allowed us to take limits separately of the 3 terms here. So n plus 1, right, times 2n plus 1 over 6n squared, okay, minus the limits for n to infinity on this one right here, n plus 1 over n squared, and plus the limits on this one, 1 over n squared. Right? And then I don't need this graphical illustration any longer. Leave that out. Okay, so what do you guys see? The first term maybe is a little all over, but what do you see in these 2 terms right here? What's the limit going to be? 0, right? See, this is clearly, right? Because as n gets larger, this whole thing here goes to 0. What about that one right here? It's also going to go to 0. Because it's a polynomial with lower degree on top, right? And higher degree at the bottom like that. You see, at this level, yes, we can start going quick like that, right? It's still not the formal way of how you prove limits. But at this point right here, we don't prove limits anymore. We assume we are fluent with limits. So yes, that goes to 0. Simply as a rational, right, with lower degree on top and higher degree at the bottom. We've learned that experience from Calc 1. Sounds good then? So that means we got these 2 becoming 0. So what about the leftover n plus 1 times the 2n plus 1 over 6n squared right here? What do you see? Right now it's in factor form. It never hurt to multiply it out. Okay? But don't you agree with me that it's also a rational, right? But numerator has degree 2, because n times n, at some point n times n is going to be a degree 2, right? Degree 2 at the bottom too. So that means what? They have equal degrees, right? So what's the case when your rational having equal degrees? When you take limits to infinity, it's the ratio of the 2 leading coefficients. So 1 times 2 is giving me a 2, right? And then over 6, right? So that reduces down to 1/3. Does that number look familiar? And by the way, ladies and gentlemen, yes? So the problem started out with one simple setup. Because it's right here. I just wanted to remind you guys, ultimately we're calculating the value of this definite integral. See what I'm saying? No? With only one starting point, and the rest of that all of a sudden turns into sum and sum and sum, right? Taking limits work like that. See what I'm saying? No? And then we ended up with 1/3. We ended up with 1/3. And so we may have lost track of what we were doing, but now you have to understand, at this point, it means that the integral from 0 to 1 on our function x squared, okay, over the interval from 0 to 1. That integral, the precise answer, is 1/3. Is that? Okay. And then I gave that geometric interpretation of that, right? When we're inside of that interval for this function, we give 0, 1, right? The accumulation happens like this. We're accumulating all those heights, right? With thickness, height is thickness. The stripe has height and thickness. That's why as I keep accumulating it, we get an area. Okay? So this integral does turn out to be the area. That's why the other day I was telling everyone that the area here is a 1/3, and I'm talking about precisely 1/3. Okay? Right? And so in the end, see, I told you the other day, and now you already found it just 2 days later, right? You guys found out the answer again, right? That this area equals 1/3 exact. I mean, not an approximate, real answer. Okay? So for you guys here on your own time at home, I would like to have you repeat the example if you can, right? But right here, use right, for you guys right here, as you can think of that as an FYT right here, okay? For your triangle. You want to say now instead of using LN like I did, right? I want you guys to use RN. Okay? It should turn into the exact same answer as we had. Okay? It's just a different, slightly different setup right here. You're gonna have to use XR right here. Right? And then, if possible, also do MN like that. Okay? And then feel free to come see me at office hours if you face any algebraic struggle and anything like that. Okay? But when it gets into this, it's all about the algebra and we manipulate the sum. Okay? Yes?
Question, I know you probably hate this question, but will this kind of analysis be on the test?
Oh, sure.
Okay.
Yeah, I mean, this is how the formal learning. It's not just about, I mean, like I said, if we learn things outside of the class, people can tell you so many directions and maybe some fast way of getting it, but we got to learn that this is where originally it came from. And you got to understand that it took mathematicians nearly 1,000 years, right, until Isaac Newton's time, and then that came up with the quick, faster methods that later on you guys will learn. But before that method came out, this is the only way. This is the only way. Okay? And so yes, at some point for you guys being a formal math student, we have our right to actually learn how to do this method. Okay? Any other questions? And yes, it's not anything that comes in half a minute or anything like that. Okay? It's definitely got to be some tedious work, but we'll get to the exact and the final result.
The question is, if there's a faster method discovered, then why is the slower method still being learned? When it's not as efficient as the faster method.
It's not about, because you're here not about to learn how to do it. You also learn, about the logic where it came from. See what I'm saying? Huh?
Right.
Because if I just, I mean, for any instructor, we just simply hand out to you the faster method, and you're going to even eventually, at one day, some generation is going to become completely ignorant about who came up with that and how important that was for your work. See what I'm saying? Yeah? Right. All right. And for here, you guys are still beginning, so there will be classes out there way above our level right now, but there are still classes where even the fast method doesn't solve the problem. You're still going to have to go back to this roundup method for you to get things done. See what I'm saying? That's why we still need to know, as a formal calculus student, we still need to know how to go through the limits process.